And then today we'll go into the actual definition of a deep learning model. We will see how the deep learning model can be defined in a notebook and some of the problems that we have solved earlier, like classification and regression, how these models can be, how those problems can be solved with the deep learning models. That's what the agenda for today is. Just to revisit a few key concepts. Yeah, the simplest version of the deep learning model or the network is the what is called as perceptron. Now, as we have seen that deep learning is a model which is based on the neural networks. It is called a neural network because it has some similarity with the biological neural networks. And the neural network is comprised of different computation layers, starting with the input layer and ending with the output layer. And in between, we may have different computation layers, which are called the hidden layers. Now, these computation layers may differ based on the purpose of computation, and depending upon the type of computation which is done, the names of the layers would be different. So we have already discussed about the fully connected layer or the dense layer, where each of the inputs coming from the previous layer contributes to the computation of the different neurons or different nodes in the subsequent layer. So all these inputs are multiplied with certain weights, and then these are summed, and then we arrive at some value, and on that value we apply an activation function. That is what happens inside the layer. How many layers you want to have, and how many nodes or how many neurons you want to have in each layer, that is a part of the definition of the deep model architecture, which we will see today. So for a quick recap, deep learning is one of the types of machine learning. The differentiating factor here is that deep learning runs on the neural network. What is neural network? It is a series of computation layers, starting with the input layer, ending with the output layer, and in between, whatever layers are there, they are called the hidden layers because we don't have a direct visibility into that. What we directly see is the input and the output, and therefore all the intermediate layers are called the hidden layers. What are these layers? These layers are comprised of, all the hidden layers are comprised of certain computations. These computations can differ. So if we are doing the image processing, then the computation is done what is called as the convolution. We'll talk about that later. So that's a different type of computation where on all the pixel data we apply certain filters. Then multiplication is done between the pixel values and the filter values, and that process is called convolution. When we process the natural language, and so in the NLP, a different type of computation would happen, which is called the recurrent network, where it's not just passing the information from one layer to the other, but the computation which has been done in the previous instance, that will be used in the next round of the computation. So there is a feedback network there. Those kind of things will be used when we are processing those things where the sequences are very important. But at this point of time, we should understand that the computation process in the hidden layers could be different depending upon the purpose for which we are creating the deep neural network. So, but still all these hidden layers, they will comprise of certain neurons. The computation process for those neurons would be different. Why do we use deep learning network or the neural network or the artificial neural network? The reason is that it handles the non-linearity and the irregular patterns in the data much better compared to the classic algorithms. And since most of the data in that we receive in the business or even uh, from nature, like genetics or the data on weather, any kind of data that you see, it's very unlikely that it will always have a linear or a very regular pattern, like a elliptical or a circular pattern. Many of the times, or most of the times, the patterns, the underlying patterns in the data will be non-linear and it will be irregular. It is because of that that deep learning algorithms are becoming more and more prominent. They are getting used more and more because it can handle this non-linearity much better. And the fact of the life is that most of the data that we receive is non-linear in nature. So it fits in very well. It is able to explain the underlying structure in a much better fashion for most of the data sets. Why it is able to explain those non-linearity and the irregular structures better? Because we have the provision of sorry, the provision of introducing the non-linearity through the activation function. As we have seen, that the computation can be done for the values, which is the sum that we are finding out. Then we apply an activation function. This activation function could be a softmax, or it could be a tanh, or it could be ReLU. So these are the different, and there are several others. These are the different types of activation function that we can use. When do we use which activation function? We will see that later. But we have seen the simple examples in the computation that we were doing earlier on the Excel sheet also, is that after we have summed the values which we derive by multiplying the weight and the input value, we apply an activation function. That activation function creates the non-linearity, or it is able to capture the non-linearity much better. So deep learning works on artificial neural network. Network is comprised of different layers. Each layer is a computation layer, and that computation can be done differently based on the purpose. Why deep learning is becoming more and more useful and prominent? Because most of the data that we receive has irregular data patterns, and that kind of pattern the deep learning models are able to identify much better. They are able to identify that much better because of the it can handle non-linearity much better compared to the classical model. And non-linearity is uh, created, or it's processed because of the introduction of the activation function. So every time that we introduce the activation function, then we are able to handle the non-linear structures much better. If that activation function is not there, then even if we have a series of linear computation in each hidden layer, as we have seen earlier, that eventually that could be compressed into a single linear function. So a combination of the linear functions can be reduced to a single linear function. And therefore, the activation part is a very important part. Because of that, it is able to handle the non-linearity much better. And because it is able to handle non-linearity, the deep learning models are much better in explaining most of the data set and the underlying structures in that data set. So that's the context of the neural network. The process which happens is that the computations start from the hidden layer one, where the inputs are received, where we receive the data from the input layer that is multiplied with some weight. Then we arrive at the sums for each neuron. We apply the activation function, and whatever value we receive, that is again used for computation for the next hidden layer. This process is called the forward pass, where we are doing some computation in each layer. Then we are passing the information for the further computation in the subsequent layer. This process until we reach the output layer is called the forward pass. Just as we do in the other kinds of machine learning computations, after we have reached the output layer, the system is making some prediction, the system is giving us some value. That value we compare with the actual value, and then the difference between the actual value and the predicted value is the error or the loss. So once we have this information about the loss, then the back propagation, or through back propagation, we see that how much was the contribution made by which neuron to this loss. And then through the optimization process, which is the back propagation, we adjust the values of the weights, and then we go backwards. So from output layer, whatever is the loss, that loss will attribute to each of these neurons. Then the weights would be adjusted. Then we go back and see that if the loss, the attribution of loss for a given neuron, in this case, whatever you are seeing on the screen in the hidden layer 2, so whatever loss we estimated or whatever loss we computed between the actual value and whatever value we received in the output layer, then we attribute that loss to these neurons, these individual neurons, and then the same process is carried forward in the reverse direction. And then we see that if this is the loss for neuron 1, 2, and 3, how much of this is attributed by each of these neurons in the previous hidden layer. So that process is called the back propagation. So in each of these neural networks, there would be a forward pass where we compute the values and we go on doing it until we reach the output layer and we have an output value. Once we compute the loss, then based on the uh, loss function and the back propagation methodology, we go on attributing the losses to the previous neurons, and then we adjust these weightages so that when we do the next round of computation, we hope to receive a lower loss. That is, the prediction would become closer to the value that we have. And we have seen that the back propagation uses two simple concepts from the calculus, and that is the differentiation, which gives us the gradient of each of these neurons, and the chain rule, because this loss needs to be propagated, or the attribution of that has to be done across all the hidden layers. So the chain rule and the differentiation are the two concepts being used in the back propagation. So that's how the network works. Now, having understood that, we also saw that one of the other differences when we come to the defining the algorithm or the solution would be that in the uh, when we were using the regression or the classification as per the classical networks, then the steps that we are following is to identify which libraries to import. From that library, which are the, we create an instance of the model. So from those library, we select the model, we create the instance of the model. After we have created the instance of the model, we train the model mostly by using the fit or the fit function. And depending upon whether we are doing regression, if we are doing regression and classification, then we give the x and y values for the training purpose. If it is clustering, then we give only x values, or the only features are given for the clustering purpose. But the process is the same. We identify the library, we identify the model, we instantiate the model, we train the model, and then we receive the predictions, and then we see that how good or bad our prediction has been. That is the process which is common and which we have worked several times in the past. An additional step what would be required in the when we are working for the solution with neural networks is that we have to define the architecture of the network. And when we say architecture of the network, how many layers do we want to have, what is the type of the layer that we want to have, and when we say type of the layer, whether it will be a fully connected layer or a LSTM or GRU layer, which is a variant of the recurrent neural network, or we are going to have a convolutional layer, which will be required if we are doing image processing. So we have to define how many layers we want, each layer, how many nodes that we want inside, or how many neurons do we want inside the layer, and what is the type of computation that you want to do in the layer. That is what, so that architecture of the neural network will be an additional activity that we need to perform when we are creating a solution using neural network, and that is what we'll see today. So let me open a notebook. Yesterday we also saw that these computations are basically matrix operation, and matrix operation is done very well in the graphic processing units. So CPUs, they are not adapted, or they are not really designed for doing the matrix computation as fast as the GPUs. And we also saw that if you are running this in Colab, you should go and check that whether the GPU is available to you or not. And that we can do by, you should click on runtime, then say change runtime type, and then you will see that whether you are using GPU or not. If not, then we'll select the GPU here and say save. So now the GPU is available. You are seeing that after the selection, it is connecting and allocating again. So we are getting, the system is allocating GPU computation space for this notebook, and that would be helpful, or the speed would be higher if we are using GPU for the deep learning network. So first we do the imports. So here in the imports, we will now start working with another set of libraries, which is called TensorFlow. So earlier we had used the sklearn library for most of the uh, classic algorithms that we have used. Different types of regression function, different types of classification models were imported from the sklearn library. Now for the deep learning, we will work with the TensorFlow libraries. So there would be certain differences in the syntax, but syntax, as you see, that the good help is available here. And therefore, whether you are using the sklearn library or TensorFlow library, not much of a problem, but of course, there would be certain additional syntax that you need to learn. Uh, so we are importing the TensorFlow library, which will contain the different libraries and different models for running the deep learning network. So we are importing TensorFlow, we are importing Pandas, we are importing Matplotlib for visualization, NumPy for certain other computation, and sklearn will still use wherever required for scaling and a few other functions. Um, Scaling is available in TensorFlow also, but since we have already become familiar with using uh, sklearn functions for scaling and a few other things, we'll continue to use that so that you don't really get into the overload of learning syntax or for the same purpose. How it is done in TensorFlow and sklearn, it might be good to know, but you always have the access to all these libraries, so we can always continue to use those functions from sklearn which we have used earlier. So what we'll do today is that earlier we have done the experimentation on the digit database. That database contained the images of different digits, and we were doing the classification based on the algorithms which we imported from sklearn. So different types of classification algorithm, and all of us have seen that. Different types of algorithms using the decision tree, random forest, SGD classifier, and a series of other classifiers we have run on the digit database, and we have seen that some of them are giving very good results and some of them were not giving that good result. We will see that if we compute the same, if we want to classify these digits, or if you want to train our models in identification of these digits using the deep learning network, then how will that be accomplished? That's what we'll try to do today. So after having imported these libraries, then we import the data set. Now we will import the same data set as we had imported earlier for the digits. This time, I mean, the same data set is available in sklearn, the same data set is available in TensorFlow. You are seeing here another thing which is called the Keras. So Keras is actually a layer above the TensorFlow libraries, which is which simplifies the use of the TensorFlow libraries. So Keras is it's not just a UI layer; it does much more. But the Keras is a layer on the top of TensorFlow libraries, which makes it much easier for us to access the different functions in the TensorFlow. That's why we are saying here, if we are importing Keras here, so we are saying from TensorFlow, import Keras. So Keras, above the TensorFlow basic libraries, we have different types of layers on top of that, which make the use of the TensorFlow libraries much easier. So for the end user, we don't need to use TensorFlow directly. We can use Keras or we can use TF-Learn, and there could be certain, and there are other libraries which are built over TensorFlow, so with different names. So for example, the uh, Microsoft or Facebook, they also use the functions of the TensorFlow, and there are several um, set of libraries for using. So we will use uh, Keras with TensorFlow or TensorFlow with Keras. So the UI part that we'll use will be Keras. So here we should remember here that TensorFlow is the library that we are using for deep learning models, and Keras is the UI or the layer above TensorFlow. So from Keras, we import the same data set as we had done earlier. Earlier, we imported this digit data set from sklearn library. The same data set is available in the Keras libraries also. So here we get the xtrain, ytrain, and xtest and ytest from the Keras library. This is the, so let's see what is there in xtrain and ytrain. So if you remember, we had 70,000 records in our digit data set, and the shape was first 60,000 records were for training purposes, and the remaining 10,000 records were for the testing purposes. And each of the record was having a dimension of 784 when we imported in sklearn. This was a 70,000 uh, observations, and each observation was having 784 features. And these 784 features represented the value of each pixel in a 28 by 28 image. So 28 into 28, that becomes 784. So the Keras, when we imported the same data, and let me also open that notebook so that it becomes easier for you to compare. So we had used digit data set. So all the name of this notebook I am showing is the fashion data set, because the fashion data set also we can run the same thing, but today we will run with the digit library. we had used this notebook for understanding how classification is done. This notebook you must be familiar with because this is what we had used when we were understanding the classification. So we are importing there. And then we were importing the data from the sklearn. So we'll run the same process side by side by using the sklearn libraries for classification, and then we'll do the same process using the deep learning. So you will be able to also compare and see the difference and how do we define a deep learning network for performing the same function as we have done using the classification function. So you would be able to compare the two and see the differences. So here also we are importing the same file, which is the MNIST digit file. And we'll see that we are now importing that into X and Y. And we can here see the shape of X and Y. There should be 70,000 records and 784. This is what I was mentioning. That when we are importing the data here, the format is slightly different when the same data is given in our sklearn library. It has 70,000 records and 784 features. And these 784, if you see, all these are the pixel data. So from pixel 1 until pixel 784, this is what the data is given to us. So the value of each pixel of the image of the handwritten data is given to us when we are working with the sklearn library. And where does this 784 number comes from? Because we saw earlier, let's go through all these steps so that we can draw the image just for your reference. So we saw here that what we have as the Y values or the labels is the value 0 to 9, and these are the number of records which we have for each digit. So there are 6,903 records for digit 0, or we have 6,903 images of digit 0, and similarly all these different numbers that we have. Yeah. So after seeing this, we just want to see that what these images are. So these are the type of images we had. And when we are, since we have been given 784 data of the 784 pixels, and we need to draw an image, we were converting that through this reshape command when we want to see the digits as 28 by 28. So 784, so I have a straight line number of 784 that is being converted into a matrix of 28 by 28. So 28 by 28, if you see in these images, if we go first row 1, then that will be 28. Then we go to row 2, there will be 28 pixels. Row 3, 28 pixels. Similarly, we have 28 different rows. So we have 28 different rows and 28 different columns. And each of these, so So in that matrix or in that table, I have a value for each image, uh, value for each pixel. That is what is represented as 784 pixels. Okay. So this is what we had got. This is the information that we had in the sklearn data. And then here, since the data is X and Y were having 70,000 records, we are doing the X train and split into X train and X test, Y train and Y test. And we are taking the first 60,000 records and we are doing a min max. So since the maximum value of a pixel is 255, so it goes from 0 to 255. You want to do min max scaling, which can be done simply by dividing the numbers by 255. That's what we are doing here. So now I have got the X test as 60,000 and 784 is the number of pixels. In my testing data, I have 10,000 records and I have 784 pixels. And in the labels, I have the label for each of these 60,000 records for the training data, and I have the labels for the 10,000 records for the testing data. So these are the 4 files we have got. Now, as we come to when we import the data from the Keras libraries, the processes that we did is already done. So it already gives you the 60,000 records, but the difference that you see is that it's already reshaped into 28 by 28. So 784 pixel. Earlier we received the 2-dimensional data, which is 60,000 records, and each record or each row or each observation is having 784 pixels. The data that we are receiving now from the Keras library is the same data, but the shape is different. It is coming into a 3-dimensional matrix where each record is having where each we have 60,000 observation. Each observation, so it's an array of an array of an array. So let's see here. How does it look like? Okay, it is X train. So if you see here, if we see the one record of X train, what does it contain? It is, so one record, if you see here, these are the 28 values or the values of the 28 pixels. And then we have 28 of these records here. So if you count each of these, it will come to 28. So the data that we have been given is in the shape of 28 by 28. Now the same thing, if you see here, it is, so all of these, if you count, it will be 784. So when we see the same data here, in say X train, and we see the same record here, now that we have done the scaling here, everything is between 0 and 1. We can, now we already done the scaling. Okay. So here, if you see, this was the record. As we move from here, we had 784 records, 784 features. Now the same data we are seeing in a 28 by 28 matrix. So by now you are aware that, let me try to explain to you that what is happening here. So what has been given to us? One record. I mean, here we'll not take 784. Let's just take a small value. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we'll just put that as, we'll just take 9 of these. So what is given to us in the data set that we imported from sklearn is that we have, suppose here, 9 different, the values of 9 different pixels. Assume that the image is only 3 by 3 pixels. This is how it is represented in the sklearn library. How it is represented in the Keras is like this. So the same thing. So this one is that each record or each observation is having 9 different pixels. And if you want to reshape it into 3 by 3, this is how the matrix becomes. Okay, so the representation in the sklearn dataset is like this. Representation in the Keras dataset is like this, but the values are the same. So converting one into the other shape is achieved by np.reshape. So we can always reshape, and I'll show you. Maybe it would be good to see what this reshape does. So for example, if you say here and here, and we'll create one. So suppose this is or let's create that as an array. We'll just take 4 of these and then we'll reshape into. So now if you see here np.shape a, so it shows that this is a one-dimensional array which has 4 elements. Now so here you see the all the help is available. So we'll define here a, and then the shape is let's see if this command works. This is what it does. So I have here a single dimensional array which is 1, 2, 3, 4. Now this is the shape of this one is that it contains a single dimension. It has 4 values. Now if you say reshape into 2 by 2, it will reshape the same data. So first 2 will become the element number one, or the first list in the array. So this is an array of an array. So if you see, it converts this data, which is a single array, into two arrays, and each array is having two different elements, and that's where the shape becomes 2 by 2. So a single array of 4 elements is getting converted into two arrays, each having two elements. That's what the reshape function does. This is what is being done for the image also. So the image is having actually 28 by 28 shape. So uh, the original shape of that is like this, and then we can convert that into a single uh, array of 784 pixel and so on. So what is happening here is that data that we are receiving from the Keras library is already converted into 28 by 28 array. So each image, as we have seen in the previous picture, each image is having 28 pixel horizontally, and there are 28 such rows of each pixel. Okay, so it would, each of our images is having some random some value of each pixel, and in the sklearn dataset, you are giving the information like this. In the Keras dataset, the same information, but you are being presented in a different shape. Okay. So having seen that, let's go down. So here we have seen that it is a single array of 74 elements. Now after that, what we had done was to import the library from the sklearn, or import the model. So this is where the import is happening. This is where we are creating the instance, and this is where this one is not really relevant because we're just giving a name to that. So that's okay. So what we have done is identified the library, imported the model, created the instance of the model, and having done that, we will train the model by calling the fit function. So we experimented with, if you recall, we experimented with different types of models, and each of these model gave us different accuracy that we'll see. So now we will train the model, and for that we call the fit function here. It is model.train, and since this is a classification exercise, we are providing the xtrain and ytrain as the input to the model. And after we do the fit, or which is after we perform the fit function, which does the training of the model, then we will make the prediction. So here right now the system is is training the model, and we have discussed several times earlier that what does it mean to train the model. The training the model means that we are optimizing it and saying that how the uh, difference between the prediction and the actual data can be reduced. So it does several iteration, and then we find out the. So prediction also has been done. These are some of the warnings which we can actually avoid. The total time taken was 34.47 seconds. After we have done the training and we have now got the predictions, we can see that how the actual data and the prediction actually compare, and this gives us that what the prediction has been. So the first one is showing, so in this one it is showing first what is the prediction and what is the actual value. So after we have trained the model, and after we have asked the model to make the prediction, we see that in most of the cases the actual value and the prediction are matching. So here if you see, there is one record which 6 is being, so our prediction was that this number is 6, the actual value was 5. All the rest, I mean, I have taken the first 10 records, it is actually matching. Then we can also see that out of the total test data that we had, 10,000, there are 742 records which are not matched. It means that our prediction about these 742 items were not really matching. And then we also saw some of the examples of the data where it was not able to predict. So for example, this item is actually 7, but our model predicted that as 9. This was actually 3, but our model read that as 8. This was actually 8. Our prediction was this is 4. Some of these you see is that even visually it is not that easy, and all these numbers are not really written very well, because all these are handwritten digits. But still, our performance is very good, because out of 10,000 records, only 700 records is not matching. And then we see that our score is actually 92%. It means that 92% of the times our model was able to identify the correct digits. Now let's see if you want to do the same classification using a neural network or the deep learning model. Okay, so now we have got the data. We have 60,000 records in the training set. But the shape of this is a bit different, and we'll see that how do we handle that. Okay, now we have done the scaling there. We had divided that by 255. We can do either the same way, or we can, in this case, we can divide the number by 255, or we can import the scaling function from the sklearn library, and then we can do the fit transform as we have seen earlier. Okay, so here I mean, this code can be written in a more simplified way. And as I have mentioned earlier, that when you're writing the Python code, it is more important that the code should be readable by you and the others. Okay, so here I have written the code. Maybe this is a bit more complex way of writing, but what is happening is that we are the sklearn library. We have seen in some instances earlier that sklearn library works only on uh, two-dimensional matrix. But the data given to us is actually three-dimensional. It is 60,000 by 28 by 28. So it is three-dimensional data. So our scaling libraries, they don't work on the three-dimensional data. So what we need to do is that convert this into two-dimensional data, and then again reconvert that into, after scaling, we reconvert that into three-dimensional data. That is what I am doing here. So if you see, the reshape is being done twice. So first I reshape into two-dimensional data, perform the fit transform, and then perform the reshape, or bring that back into the shape which was there of the xtrain.shape. Since right now the focus is on how to define the neural network architecture, I'm not going into this process. If you are able to understand that what is happening, well and good. Otherwise, we can take it up in this subsequent session. So what is being done here is the same scaling function, what we are doing here. So that is, we are dividing at some place, we are dividing it by 255. Yeah, we are dividing the 255 here itself. So it brings all the pixel values between 0 and 1, because the maximum value is 255 and the minimum value is 0. So either, in this case, either we can do this, but the better method is to call the scaling function. So we are calling the min-max scaler, which will anyway will bring the entire value between 0 and 1. So we are scaling the xtrain data, we are scaling the xtest data. And after that, now my data set is ready for optimization, or ready for being fed into the neural network. Okay, so this part is again to show that this is the same kind of images that we had, same kind of data we have here, randomly chosen some images, so we are convinced that it is the same data set. Now we come to the definition of the model. This is where you will see the difference. So earlier we just imported the inbuilt models, but here we need to define the model. Okay. Let's define the neural network architecture. This will be an additional step every time that you work with a deep learning model. Okay. So what do? We define a model. We have just given a variable name as learning model, or in short LM. Now we say that this model is actually a sequential model. Sequential model, as we have seen earlier, that different types of models we can define. Sequential model means this is a feed forward model. So one layer will do the computation and then feed it forward to the next layer. That type of model is called the sequential model. So we are first defining that from the Keras library, import models, and from there you get the sequential model, and that we are initializing as with a variable name LM. So that model has been defined. Now if you go back to our architecture of the deep learning, I'm just trying to make it bigger. So if you see, now we have to define each of these layers. Okay. So after having said that this is a sequential model, it means that all the computation will be passed on one by one to the rest of these things. And that would be the most common model that we would use. After having said that this is a sequential model, now we define each of these individual layers. So you will have to define each of these individual layers. Why? Because we need to say that how many layers we want, and what is the number of neurons that we want in each layer, and what is the activation function that we want in each layer. So these are the things that we need to define. And that would be the additional step when we work with the neural networks. So now having defined this model, we can go on adding these layers. So we say add one layer to the model. And what is that layer? This layer is we are adding as the flattened layer. Why do we need a flattened layer? Because the data that we have got now is in the shape of 28 by 28. So this is a two-dimensional data. We need to flatten that into a single dimension, and it will convert this each 28 by 28 data into 784. So it actually brings, this layer is actually bringing the data back into the form in which we had got the data from the sklearn library itself. But here, since we have got the data in 28 by 28 in the that we have got from the Keras library, if your data was, if we are using the same file, and we can always use the same file which we have got from the sklearn library where the shape was 60,000 into 784, then this step is not required. But since our data is in the shape 28 by 28, we are flattening that data, and when we say flatten the data, it will convert this 28 by 28 shape into 784 by 1. Okay. So that is the first step that we are doing. Then we are introducing one dense layer, or we have seen that the fully connected layer is also called the dense layer. And what do we mean by the fully connected layer? The fully connected layer is where every input from the previous layer is contributing to the computation of every neuron of the next layer. So as you can see in this diagram, we have 4 different elements in the input layer: x0, x1, x2, and x3. And each of these 4 is contributing to the computation of the 3 nodes or 3 neurons that we have inside the hidden layer. So this kind of network is called a fully connected network or a dense network because the computation is very dense. So, but for this computation, we are taking the input values. Then the second element which goes into computation is actually the weightages. And these weightages would be assigned and optimized by the algorithm. We don't need to worry about that. That is what the deep neural network and the optimization process actually does. So our job is to define what the input would be, is to define how many layers that we want, is to define how many nodes that we want in the layer and what would be the activation function. Okay, so we come back to this one. We have said that let's create a sequential model. Then we are saying that the first layer would be the flattening. So first we flatten the input that we receive. If your data itself is in a, you know, 784 pixels and not in the 28 by 28 form, this step would not be required. Then we say my first computation layer is a dense layer. It means that it will have, it will take input from every element that we have in the previous layer, or every uh, feature that we have. Now this 300 is actually saying that we want 300 nodes in this layer. So if we go back to this architecture, so these here we are depicting 3 nodes here in the first layer. Now we are saying that I want 300 nodes. And the activation function would be ReLU. ReLU is the rectified linear unit. What it does is that if there is any value which is after the computation of this layer, if this aggregate value is less than 0, then it converts that value to 0. And if it is more than 0, it leaves it as it is. So it still brings about a non-linearity because it is converting the values which are less than 0 into 0. So ReLU is a very simple activation function, which simply says that if the value is less than 0, make it 0. If the value is more than 0, leave it. Okay. So activation, as we discussed yesterday also, that in most of the cases, the activation function that we will use in the hidden layers will be ReLU. In the output layer, we may use different types of activation depending upon what is the kind of output that we want. But in most cases, not in all cases, in most cases, the activation function in the hidden layers we will use as ReLU function. I think that is also the default. Let me check if that is the default. So here, as we see here, yeah. So no, default is activation is equal to none. So we will have to define that. So since we want ReLU to be the activation, okay. Now just to recap that why are we bringing the activation function as ReLU? Because this is what brings about the power of the neural network. This is what brings about the non-linearity. Okay, so we are saying that we will have the first computation layer. So my input layer becomes now 784. So input layer will have 784 features because 28 by 28 we are flattening, and when we flatten, the 28 by 28 will become 784. So this one becomes my, so my input layer has 784 features after flattening. Okay. Now then we define our first hidden layer, which will have 300 nodes. Okay. So each of these 784 pixels will contribute to the combination, will contribute to the computation of these 300 nodes which I have in the first layer. Then we are saying that, okay, give me a second layer which will have 100 nodes. So the second layer that we are introducing here, we'll have 100 nodes, not 300 nodes, but 100 nodes. Then we are saying, let's get a third layer, which will have 50 nodes. And then the output layer. So the last one is the output layer. And output layer will have 10 nodes. Why 10 nodes? Because we have 10 different digits. And the output that we want is that the system should be telling us that which of these 10 the input actually belongs to. So if the input image was of 9, then output image should be saying that out of these 10 digits that we have starting from 0 to 9, this is 9. So in the classification, whenever we are doing the classification in the output layer, the number of nodes or number of neurons that we'll have should always be equal to the number of classes or number of categories that we want the input to be classified. And that's why we are keeping the last layer, which is our output layer. So in the last layer, which is our output layer, we are defining here as 10. So the number of nodes here would be 10. If it is regression, then the number of nodes would be only 1 actually. So now we have 10 different neurons or 10 different nodes in the output layer. Okay. Having defined that, having added all these layers to our model, now let's see the summary of these models as to how this model actually looks like. And we need to understand a few things here. So now it says that this model that we have defined is a sequential model, which is what we wanted. Then when we flatten it, we get 784 nodes or 784 neurons or 784 features in the input layer. Now in our first dense layer, if you see here, there are 300 nodes. That is what we defined here. Now the parameters, if you see, parameters is 235,500. It means that when we are coming to the first dense layer, we are dealing with 235,500 different parameters. And how does that come about? That come about because each of these 784 pixels that we have or the nodes that we have in the input layer. So let's see here, we'll do a quick maths here. So from input layer, we have 784 different elements. And now in the hidden layer 1, just call as H1. Then we have H2, then we have H3, and then we have the output layer. This is the kind of architecture we are defining. And the number of nodes that we have, these are the number of neurons that we have in each layer. Now if you see parameters, when we come to this layer, each of these 784 is used in computing each of these 300, isn't it? So if you go back to this architecture, each one is going into this. So the number of parameters, if you see, this will be, in this case, whatever is there on the screen, it will be 4 into 3. So there will be 12 different parameters that the system has to deal with. And then we have a bias input. This is what we have said that in the regression that we have seen, this is the equivalent of the constant. So in the regression, our formula was y is equal to bx plus c, and c is the constant, which we are calling as the bias input. So this bias input will go into each of these neurons. So the number of the bias inputs will be equal to the number of neurons that we have in the hidden layer. So parameters will be this, and then the bias neurons, bias parameters. this will be equal to the number of neurons that we have, and if you take the sum of these two, that is what we get, 235500. It means that in the computation of the first hidden layer, the neural network will actually deal with or will compute 235,500 different parameters. So you see how computationally intensive these deep neural networks would be. Now, when we come to the second layer, we have defined that this will have 100 neurons, and there are 300 neurons in the previous one. So each of these 300 will contribute to the computation of these 100, and therefore the number of parameters that we will have is 300 multiplied by 100, or 30,000 here. And how many biased neurons we'll have is depending upon how many nodes that we have here. And therefore, in the next layer, we have 30,100 different parameters. Let's see here what is. So in the next layer, we are dealing with 30,100 parameters. The same thing would be in the third layer. So in third layer, we have said that we will have 50 different neurons, and therefore we will have 50,000 computations. Each of these 100 neurons will feed into these 50 neurons, so we get 5,000. And then we have 50 biased neurons, a total of 5,050. And since in the output we are having 10, so here this will be 510. And therefore total, if you see, the system will actually work with these many different parameters. 271160. So just in 3-layered network that we are defining here, we are dealing with 271,160 different parameters that the system would compute in the process of optimization. Okay. So now we have defined the model. What we have done here is only define the model. Okay. Now, having defined the model, another step which will be required is to compile the model. So maybe I'll segregate that into 2 different lines of code. Okay. Having defined the model, we need to compile the model. And while compiling the model, we need to define what is the optimizer that we are going to use. So in the here also the different models that we have here, logistic regression or the risk classifier, MLP classifier, these are the different types of models that we had used earlier. And these models differ from each other because the optimization process that they internally have is different. So here, we need to define the optimizer, and there are different types of optimizers available. We need to define what would be the loss function. As we have seen earlier, that loss can be computed in different ways. When we were running the regression, 2 ways that we were computing the loss. One was the R-square and the second was the RMSE. When we were discussing the classification, we have seen that the loss can be computed with either precision or recall or accuracy or F1 score, and there are certain other ways that we can compute the loss. So here we also need to define that this optimization will be done around which loss function, whether it will be accuracy or precision or recall. So here we are using the accuracy part, and that is right now, that is called the cross entropy loss. We have seen this earlier, the Gini and the cross entropy. The loss would be defined as the cross entropy loss. and the metrics that we are using is the accuracy. So, sorry, I switched in the last time. The metrics is the accuracy. So it will compute the accuracy, and how the accuracy would be computed. The loss function would be our cross entropy loss. So this cross the entropy also we have discussed earlier, that how the entropy is computed. So these are the three things normally we'll have to define while you're compiling the model. Which optimizer you are going to use, which is the loss function that you want to use, and typically for the classification we will use the sparse categorical cross entropy. So if we are doing a classification, multi-class classification, then this is the loss function to use, sparse categorical cross entropy. If we are classifying our objects only into two categories, that is the binary classification, then there are other loss functions to use. And here we can define that whether you want to go with accuracy or precision, recall, these are the things. So we'll compile the model. So after defining the model, we need to compile the model. And after we have compiled the model, then the training function. So again, we choose the instance of the model that we have created, which is already compiled. Then we call the fit function, and to that fit function, we are passing the parameters as my training data, the features in the training, the levels in the training. Another thing that you need to define is the how many epochs that you want. Now, just to revisit the concept of the epoch, with all this data, as we go from input layer, do all the computations gradually, and we reach the output layer, we compare the results, we compare our prediction with the actual model, then we find out the loss. Having found the loss, then we go back, use the back propagation to optimize these weights. This process, once it is run on the entire data set, that is, then one forward pass and one backward pass, one forward pass and one reverse pass, one forward pass and the back propagation if we do once. It is once that is completed on the entire data set, that is called an epoch. It means that we have completed one round of computation on the entire data set. That is called an epoch. So if you don't define the number of epochs here, the system will end the operation with one epoch. So the default value for the epochs is 1. But it's important to understand, recall, and it becomes a part of your deep learning vocabulary. Epoch is performing the one forward pass and one reverse pass on the entire data set is called epoch. So we'll try with say 10. As you will see that with every epoch or every round of computation, the performance or the accuracy of the model will go on increasing. Validation also we have learned earlier. So we are saying that in every round of training, keep 20% of the data for validation. So it will actually train on the 80% of the data. After the training is done, the loss computation would be done on the validation data set. Okay, and only then it will run the prediction on the testing data set. Okay, so in the process of training, as you recall from the previous discussion, that during the process of training, we do not expose the testing data to the model, because the model tends to remember and tends to overfit, and we want to assess that how the model is performing on the unseen data, and that's where we don't expose the testing data during the training process. But how good our training is doing on the unseen data, we can also test that during the training process itself. So what we do is that from the training data itself, we take out certain part of the data, and in every round of training, we will keep some data aside. We will train that So here we are saying validation split is equal to 0.2. That means that we are keeping aside 20% of the records aside, and the model will be trained on 80% of the data. And after the model has been trained, it will validate the accuracy on the remaining 20% of the data. So that will happen in each epoch. Another thing is that we can define the batch size. As we have discussed earlier, that this optimization process will run on the mini batches. So what a system would do is that it will first pick up the 200 records. It will perform a forward pass and a reverse pass with these 200 records. So now it has got the error on 200 records. Based on that, the optimization would be done. So if my total data is 60,000, and if I define the batch size as 200, it means that the optimization process will run 300 times in one epoch. We said that epoch is when we have run the optimization process on the entire data set. Now, depending upon the batch size, so many batches of optimization or so many rounds of optimization will happen. As we run this, you will see what is happening. So now the system has started epoch 1, and you see here that 240 different batches have been run. Why 240? Because our training data was 60,000, and we said that validation is 20%. It means that training is happening only on 48,000 records. And since our batch size is 200, the number of batches it will run is 240 batches. And remaining 20% or remaining 12,000 data we have kept for validation. So now we see the results here. It has run the first epoch, and each epoch it is running 240 batches, because each batch size is 200, and our total training data is now 48,000. Because so if you see the computation, I'll just do it here. So my data size the training data has 60,000 records. Then we had said validation split is 20%, 0.2. And therefore, in each epoch, what it will do is that training size, that will become 60,000 into 1 minus the validation. So we'll have 48,000 training, and the validation size, this will be 60,000 into the validation split. So the training will run on this one. Now if I say here batch size, you defined as 200, and therefore number of batches in each epoch will be 48,000 by 200. So 240 batches it will run in each epoch. After it has run this, then it will, it will do the validation on these 12,000 records, and that will be done in one epoch. Then the second epoch starts, where it will again, with the new refined weights that we have got, now it will do the training again on the entire 48,000 records. That is what is happening here. So in the first epoch, we saw that our accuracy was only 50%. Okay, so this was the accuracy on the training data, and on the validation, it had an accuracy of 81%. So it is also computing the accuracy on the training set and the training data and the validation data. What we are more concerned about is the validation data, how good it is. In the second round, if you see, it goes up from 50% to 83% on the training data, and goes up from 81% to 87% on the validation data. So until now, we have not really tested it on the testing data. It's only from the X train file that we have. It is splitting that into two parts, and this result is on the validation data. So as you see, with every passing epoch or every round of training, the accuracy is going on from 81% to 87, 89, 90, and so on. In some cases, you will also see that there would be a dip, and then again the accuracy comes up. So we have now captured the information about how the accuracy has improved over the validation data and how the accuracy has improved over the training data. Now we can actually do a plot and see what is happening here. So we had stored all this data into our history file here. So if you see, when we were doing the training, we store all this information into history file. So all this epoch-wise accuracy scores are getting stored in the history data. And then we come and plot that. So as you can see that the accuracy is improving, it goes up to about 83%, and after that there is an incremental improvement with every epoch. And correspondingly, the loss is actually coming down. So these two will obviously move in different directions. The loss will come down and the accuracy will go up. Okay. So after having done this, then we can always see that how is it performing, or how the model is performing on the test data. Because during the training process, we had not exposed the model to the testing data, but our key criteria is that does it really perform well on the testing data. So now we will make the prediction. And then again, we see here this same thing I have done. So for maybe for the first few records, I see here for the first 10 records, what the performance has been. So I'm just taking the first 10 records, and we see that what is our prediction and what is the actual. So 7, 2, 1, 0, 4, 4. So 6 and 5 are again getting confused here, same as the previous one. Okay. This one we don't need to be worried about. Okay. So now we have run the model and we have also got the prediction. Just let me see if we can get the accuracy score on the test data. Okay, so this is how we define the neural network, and we define the the process here is that first we need to define, then we compile, and then we do the fit and predict. Okay, so that's the difference would be here. So if you see here, we got the accuracy of 92% with this model, which is more or less the same what we had got in the logistic regression model. Now the beauty of the deep learning model is that even if you run the logistic regression model several times, you will actually going to get the same result. But here, if either we increase the number of epochs, or if we make our network deeper, you will see that we will get a better result. Okay, so let's try out with here. We'll make it here 500. Let's make it here 300, and then let's make it 150, and we will introduce one more layer. This layer will keep as 50. So earlier we were dealing with say 2,71,000 parameters. You will see that these numbers will now increase even substantially. So now we are dealing with 596,000 parameters. So having defined that, we'll compile that model. And when we run, I'm increasing the epoch size to not just 10. Let's say I'm increasing this to 50. Okay. Then you will see that there should be a good improvement in the performance. Okay, so now we increase the depth of the model and we increase the number of epochs that we ran, and you see that the performance goes up to 97% compared to 92%, which is actually a very good improvement, because above 90, increasing 5% accuracy is actually a substantial achievement. And then if we plot the graph here, now you see something which is that we should notice, that when we see this loss graph here, or even the accuracy graph here, earlier we were seeing that both of these accuracy on the training and testing both was going on increasing. But here you see that the accuracy on the validation set actually stagnates around 98, but the accuracy on the training set is going on increasing. Okay, and that is something that you will always notice. Why it happens? Because this part, the validation accuracy, is not really seen by the system, because it keeps that data aside. It's not a part of the training. So as you train more and more, the system tends to sort of remember that the entire data set, and therefore the accuracy on the training set will continue to increase. But our real test is it really performing well on the unseen data? And that's where we need to look at the accuracy on the validation set, and after that we can always go back to the testing set. So if the validation score is not improving, and if the score on the training set is going on improving, that is what we call as the overfitting. It means that now beyond a point, the system has sort of started, memorizing that data, and it is at that point that we should actually stop the training. So I could give the number of epochs to 100 and 150, but actually it's not helping beyond a point, because now the validation accuracy is not improving, but the system will go on showing the increase in the accuracy on the training data. So this is something that we need to watch out for. If the accuracy on the validation set is not improving, then we should actually stop. Okay. So one of the key benefits here is that unlike the classical model, here if you increase the depth of the model, or if you increase the epochs, then in most of the cases you get much better performance. So what we'll do, I hope the process is clear. We'll definitely go through another data set tomorrow, and we will see that some 2 or 3 different iterations we will do. Then you will be very clear about how to define a deep learning model, and how to compile the model, how to train the model, and again how to get the predictions. Okay. So I haven't checked if there are any questions. Okay. So if there are any questions for today, I'll take that. Otherwise, we'll continue with our definition of the deep learning tomorrow. If there are no questions, then we'll end the session here and we'll meet again tomorrow at 7.